Time seems to slow down when you are completely absorbed. That strange stretch of a moment might be more than a trick of the mind. Quantum physics hints it could be a literal, physical truth. There exists a phenomenon so bizarre it suggests that watching something can stop it from changing. This is the Quantum Zeno Effect, where constant observation forces a quantum system to stay frozen in place. By the end of this exploration, you will understand how this quantum quirk could reshape technology and our very conception of reality. We will uncover how scientists freeze atoms with laser light and ask if ancient philosophy predicted this all along. How much of reality is shaped simply by our act of looking at it? The core idea feels almost like a magic trick. If you want to freeze a quantum particle in place, just keep looking at it. This is the Quantum Zeno Effect in its simplest form. It is the inhibition of a quantum system's evolution through frequent, repeated measurements. To understand why this works, we need to revisit a fundamental quantum rule. In the tiny realm of particles, things do not have definite properties until you check. An atom can be in a state of decay and not decay at the same time, a ghostly blend of possibilities called a superposition. It is only when you measure it that this fuzzy cloud of potential collapses into a single, concrete reality. Now, imagine that immediately after that first look, you look again. And again and again. Each measurement forces the system to reset, to collapse back into its starting point. It is like constantly asking a flipping coin if it is heads or tails while it is in the air. Your incessant questioning never gives it a chance to actually land. The classic, everyday analogy is the watched pot that never boils. Your impatient glances interrupt the natural progression, resetting the process. This effect is named for Zeno of Elea, an ancient Greek philosopher who crafted paradoxes arguing that motion is an illusion. His most famous paradox, Achilles and the tortoise, suggests that if you keep dividing the distance between them, the swift Achilles can never actually catch up. The Quantum Zeno Effect presents a startlingly similar idea, but in the physical world. Zeno argued you could never finish a journey because you must always reach the halfway point first. Quantum mechanics shows that constant observation can, in a very real sense, prevent a particle from ever starting its journey at all. But what does it mean to measure a quantum system? This question lies at the very heart of the mystery, a puzzle known as the quantum measurement problem. For over a century, physicists have debated what actually happens when we look. The most common framework, the Copenhagen interpretation, offers a stark picture. It says a particle, like an excited atom, does not have a definite state of decay until you check on it. Instead, it is described by a mathematical entity called a wave function, a cloud of probabilities encompassing all possible outcomes. This wave evolves smoothly and predictably, governed by Schrödinger's equation. It is a quiet, continuous dance of potential, but the instant you make a measurement, something drastic occurs. That smooth wave function collapses. All those shimmering possibilities vanish, and a single, concrete reality snaps into place. The atom is either decayed or it is not. There is no in-between. This collapse is not a gentle process. It is a violent, instantaneous interruption of the natural quantum flow. And this is where the observer takes on an almost magical role. The act of looking is not passive. It is an intervention that forces the universe to make a choice. This blurs a line that once seemed absolute, the line between the physical world and the consciousness observing it. Does reality truly not exist in a definite state until a mind, or a machine built by a mind, interacts with it? The measurement problem leaves that door unsettlingly open. It is this very act of intervention, this forced collapse, that the Quantum Zeno Effect exploits so cleverly. This philosophical riddle demanded a physical test. In the late 1980s, a team led by Wayne Etono and David Wineland designed an experiment to see if observation could truly freeze time for a quantum particle. Their laboratory was a world away from ancient Greek paradoxes. It was a vacuum chamber holding a single, lonely atom of beryllium, suspended in space by electric fields and cooled by lasers to nearly absolute zero. This atom was their quantum clock, and they aimed to stop its ticking. The atom was prepared in an excited energy state, a high-energy condition that naturally wants to decay to a lower, more stable ground state. Left alone, it would make this quantum jump in a predictable amount of time, but the scientists did not leave it alone. They used a precise sequence of laser pulses to interrogate the atom. Some pulses were designed to gently nudge it, to encourage that transition from excited to ground state. Other pulses, carefully timed, acted as the observer. These measurement pulses were tuned to a frequency that would only interact with the atom if it was still in its excited state. If the atom had decayed, the laser pulse would simply pass by unnoticed. Each time a measurement pulse hit the atom and got a response, it was like a detective shining a light into a dark room and confirming the suspect was still in the corner. That single act of confirmation, that flash of interaction, collapsed the atom's fuzzy wave function. It reset the quantum clock, forcing the atom back into its definite, excited starting point. The team varied the experiment. They increased the frequency of these observational flashes. When they looked very often, something remarkable happened. The atom's natural decay was suppressed. It stayed frozen in its excited state, not because it was stable, but because it was never given a moment of privacy to change. By constantly asking, "Are you still excited?" they prevented it from ever becoming anything else. The data was clear. The more they watched, the less the atom changed. Reality, at least for this one beryllium ion, had been frozen by the sheer act of observation. It was no longer a philosophical thought experiment. It was a measurable fact written in laser light. This ancient thought experiment finds a startling echo in the lab. Zeno of Elea lived over 2,500 years ago, yet his paradoxes cut to the very core of how we perceive reality. He was not a scientist in the modern sense, but a philosopher determined to defend his teacher Parmenides' radical claim. Parmenides argued that change and motion were mere illusions of the senses. True reality, he said, was a single, unchanging, eternal one. To prove this point, Zeno crafted a series of clever, frustrating arguments. His most famous is the race between Achilles, the legendary swift hero, and a slow-moving tortoise. Zeno gives the tortoise a head start. By the time Achilles reaches the tortoise's starting point, the tortoise has crawled a little farther ahead. When Achilles reaches that new point, the tortoise has again advanced, however minutely. This logic can be repeated endlessly. Achilles must always first reach where the tortoise just was, and the tortoise is never quite there. Therefore, Zeno concludes, the swiftest runner in history can never actually overtake the slowest creature. Another paradox, the arrow paradox, examines a single moment in flight. At any given instant, Zeno argues, an arrow occupies a space exactly equal to its own length. It is not moving into a new space during that instant, for an instant has no duration. So, at every instant, the arrow is motionless. If it is motionless at every single instant of its supposed flight, then when does the motion actually happen? The underlying strategy is always the same. Zeno takes our common sense experience of smooth, continuous motion and dissects it into an infinite series of frozen snapshots. He then asks us to reassemble motion from these static frames, a task that seems logically impossible. His goal was to show that if you think about motion too carefully, it dissolves into contradiction, proving it must be an illusion. The power of his paradoxes lies not in their practical truth. Of course, we see things move, but in their exposure of a deep conceptual rift. They reveal a gap between our intuitive understanding of the world and a logical, mathematical description of it. This is the precise gap where quantum physics now operates. Zeno's philosophical freeze frame, his argument that constant division halts progression, is mirrored perfectly in the Quantum Zeno Effect. His paradox asks, if you keep observing the halfway point, can a journey ever be completed? The quantum answer, demonstrated with lasers and atoms, is a resounding no. If you keep observing the starting state, a quantum transition can never begin. The ancient mind, grappling with the nature of change, accidentally outlined the rules for a technology that would not exist for millennia. It is a profound connection, suggesting that some truths about reality are so fundamental they whisper to us across the centuries, waiting for the right tools to give them a voice. Yet the story of observation does not end with a frozen atom. Quantum mechanics, in its relentless strangeness, offers a perfect mirror to this effect. If constant watching can halt change, could a different kind of watching actually speed it up? The answer is a resounding yes, in a phenomenon known as the anti-quantum Zeno effect. Here, frequent measurement does not preserve the status quo. It actively destroys it, pushing a system to decay or transition far faster than it ever would in private. This is not a contradiction, but a deeper layer of the same principle. It all depends on timing. Remember the atom suspended between two states, its wave function oscillating like a quiet internal pendulum. When you measure it very, very quickly, you are essentially sampling its condition. If your measurements are perfectly out of sync with this natural rhythm, you keep catching the pendulum at the top of its swing, forcing it back to the starting point. That is the standard Quantum Zeno Effect, freezing time. But what if your measurements are perfectly in sync? Imagine pushing a child on a swing. If you give a small push at the exact moment the swing is moving away from you, you add your energy to its motion. Each push, perfectly timed, makes the swing go higher and higher. The anti-Zeno effect works on a similar principle of resonant driving. If the frequency of your measurements matches the natural oscillation frequency of the quantum system, each measurement pulse does not just observe, it gives the system a tiny, coherent nudge in the direction it was already going. Instead of resetting the process, you amplify it. You are not asking the flipping coin if it is heads or tails. You are tapping it on the edge at the perfect moment to make it spin faster. In the laboratory, this means tuning laser pulses with exquisite precision. Scientists can set up an experiment where an atom is likely to decay, and then hit it with a rapid series of measurement pulses that are in resonance with its internal quantum clock. The result is astonishing. The atom decays not in its natural time frame, but in a fraction of it. Observation in this carefully orchestrated mode becomes a catalyst. It is a profound demonstration that in the quantum world, looking is never a neutral act. It is always an interaction, and the nature of that interaction, its rhythm and its intent, determines the outcome. The same light that can pin a particle in place can also be used to shove it violently into a new state. This duality transforms the observer from a passive witness into an active participant with a dial that can be set to either freeze or accelerate the very fabric of reality. The power to freeze or accelerate reality is not just a laboratory curiosity. It is the hidden heartbeat of the technology that orchestrates our modern world. This principle finds its most breathtaking application in the atomic clock, a device of such staggering precision it redefines the very meaning of a second. At its core, an atomic clock is a masterful application of the Quantum Zeno Effect, using constant observation to create the most reliable timekeeper ever built. The process begins with a cloud of atoms, often cesium or the even more precise strontium. These atoms are cooled to a near standstill and isolated from all external noise. Scientists then prepare them in a very specific high-energy state. Left alone, these excited atoms would eventually decay to a lower state, but that natural instability is the very thing the clock must prevent. So it bombards them with a continuous, finely tuned microwave or laser beam. This beam is not a passive light show, it is an incessant interrogator. It constantly asks the atoms, are you still in that exact high-energy state? if an atom is still there, it interacts with the light in a predictable way. But if an atom tries to decay, to slip into a different energy level, that interaction fails. The system detects this failure and applies a correction, effectively nudging the straying atom back into line. This relentless cycle of measurement and feedback is a technological Zeno effect. The atoms are given no private moment to transition randomly. They are frozen in their desired state by the perpetual gaze of the laser, which suppresses all unwanted quantum jumps. This locked-in stability is what creates the clock's tick. The frequency of that interrogating light beam itself becomes the pendulum of the clock, and because the atoms are forced to stay perfectly in sync with it, that frequency is unimaginably pure and steady. The best atomic clocks today would not gain or lose a single second in over 15 billion years, longer than the current age of the universe. This quantum-guarded time is what flows through the veins of global infrastructure. Every GPS satellite carries an atomic clock. The triangulation that pinpoints your location on a map relies on timing signals from these satellites with nanosecond accuracy. A timing error of just 1 microsecond, 1/1,000,000th of a second, would translate to a positioning error of over 300 meters. The entire system would be useless without the frozen atoms guiding it. Beyond navigation, the synchronized pulse of atomic clocks governs the world's financial networks, time-stamping high-frequency trades to prevent chaos. They enable the ultra-precise coordination of power grids and telecommunications networks. They even serve as exquisite tools for fundamental science, allowing physicists to test whether the constants of nature are truly constant, or if they drift over the eons of cosmic time. From a philosophical paradox about motion to the quantum freezing of a single atom, to the invisible signal that guides your drive home, the line is direct and undeniable. Our reality is increasingly built on foundations of managed quantum uncertainty, where watching closely is how we build a world that runs on time. This mastery over quantum stability is the key that may unlock the next computational revolution. The dream of a quantum computer hinges on manipulating the most delicate objects in the universe, qubits. Unlike a classical computer bit, which is definitively a 0 or a 1, a qubit exists in a superposition, a blend of both states simultaneously. This ghostly in-between condition is what grants quantum computers their phenomenal potential power, allowing them to explore countless solutions to a problem at once. But this power comes with an immense fragility. The moment a qubit interacts with its environment, whether from a stray photon, a vibration, or a magnetic field, its precious superposition collapses. This loss of quantum information is called decoherence, and it is the single greatest obstacle to building a practical machine. It is as if you are trying to perform a symphony on instruments that go out of tune if anyone so much as breathes on them. To build a computer, you need reliability. You need to make the fragile robust. This is where the principles of the Quantum Zeno Effect move from philosophy into high-stakes engineering. The goal is not merely to observe a qubit, but to actively protect it. One powerful technique is called dynamical decoupling. Imagine your qubit is a spinning top. The noisy environment is like a series of random puffs of air, each one threatening to knock the top over. Dynamical decoupling applies a rapid sequence of precisely crafted electromagnetic pulses to the qubit. These pulses act like a skilled hand, giving the top a series of tiny, perfectly timed taps. But these taps are not random. They are designed to cancel out the effect of the environmental noise. Each pulse effectively flips the qubit state in such a way that the disruptive influence of the first half of a time interval is exactly undone by the second half. From the qubit's perspective, it is as if the noisy world is being constantly nullified, its destabilizing whispers shouted down by a rhythmic, protective chant. This is an active, driven form of the Zeno principle. By not allowing the qubit a moment to be corrupted by its surroundings, you freeze it in its intended quantum state. You are building a cage of light and timing to shield a superposition from reality itself. But for a large-scale, fault-tolerant quantum computer, passive shielding is not enough. The system must also detect and correct errors without destroying the quantum information it is trying to protect. This leads to the even more sophisticated realm of quantum error correction. Here, the idea is to spread the information of one logical qubit across several physical qubits, creating a kind of quantum redundancy. Then, the system performs frequent, cleverly designed measurements on only some of these physical qubits. Crucially, these measurements do not reveal the actual quantum state of the logical qubit, which would collapse it. Instead, they diagnose whether an error has occurred, much like a doctor running tests that indicate an illness without directly observing the patient's private thoughts. Once an error is detected, a correction can be applied. This cycle of diagnosis and correction is a form of continuous, indirect observation. It constantly asks the system, has the quantum information been disturbed? And resets it if the answer is yes. It is a grand, automated application of the watched pot principle, but here the pot is a ghostly quantum calculation, and the watching is done by other quantum bits. Mastering this art of quantum vigilance is what separates theoretical blueprints from a working machine. The race to build a useful quantum computer is in large part a race to outpace decoherence through ever more clever applications of the Zeno principle. Success would mean more than just faster computers. It would give us machines that could simulate complex molecules atom by atom, leading to revolutionary new materials and life-saving drugs. They could crack the mathematical problems underlying our current encryption, forcing a complete overhaul of digital security. They might unlock optimization problems in logistics and climate modeling that are currently unsolvable. The future they promise is built on a paradox that to harness the fluid, probabilistic nature of the quantum world, we must first learn the art of freezing it perfectly in place. But who or what is this observer with such power? This question takes us from the clean lines of the laboratory into the foggy, contested borderlands where physics meets philosophy. The measurement problem, that deep crack in our understanding, forces us to confront a startling ambiguity. What exactly constitutes an observation? Is it the click of a Geiger counter, the flash on a computer screen, or the moment a human scientist finally looks at that screen and understands the data? The Copenhagen interpretation, the traditional framework, is famously vague on this point. It treats the measurement device as part of the classical world, a magical boundary where the fuzzy quantum probabilities collapse into a single reality. But where does that boundary lie? Is a single photon hitting a camera sensor enough to collapse a wave function? Or does the collapse only happen when the electrical signal from that sensor reaches a conscious brain? This line of thinking leads to a radical and for many unsettling idea. That consciousness itself is the catalyst that crystallizes reality from a soup of possibilities. It suggests the universe only becomes definite when a mind perceives it. This is the ultimate extension of the watched pot principle, implying that without observation, everything remains in a ghostly state of potential. The Quantum Zeno Effect, in this view, becomes a literal demonstration of mind over matter, where focused attention holds the world in place. Yet this idea makes many physicists deeply uncomfortable, as it places something immaterial, consciousness, at the center of physical law. Other interpretations offer wildly different answers, each trying to banish the special role of the observer. The many worlds interpretation takes the opposite approach. It says the wave function never collapses at all. Instead, every possible outcome of every quantum event actually happens, but in a newly branching parallel universe. In that dizzying view, when you measure an atom, the universe splits. In one branch, you see it decayed. In another, you see it intact. There is no single observer forcing a choice, just an endless proliferation of realities where every possibility is realized. So what about the Zeno effect in this sprawling multiverse? It would mean that with frequent measurement, the branching of realities is constantly steered or pinned, so that in the overwhelming majority of branches you continue to experience the same outcome. The atom stays excited not because you freeze one reality, but because you navigate a vast forest of realities down a path where it never seems to change. It is a statistical illusion of stability across infinite worlds. Then there are theories like objective collapse which propose a more physical mechanism. They suggest that wave functions collapse spontaneously when they become too large or complex, a process driven by gravity or some other fundamental force. In this picture, a measurement device simply accelerates an inevitable process. The observer is not special. It is just a very big, complex collection of atoms that triggers collapse sooner. The Zeno effect here is like constantly giving a wobbly table little kicks to keep it from finally tipping over on its own. You are not creating the stability, you are just proactively managing a natural instability. Each of these interpretations, Copenhagen, many worlds, objective collapse, is a different story we tell to make sense of the equations. They all account for the experimental data, including the frozen atoms in the Zeno experiments. Yet they paint utterly different pictures of what is really happening. This is the profound strangeness at the heart of quantum mechanics. We have a tool of incredible predictive power, but we cannot agree on what the tool is actually describing. The physics works perfectly, the philosophy is a maze. This brings us back to you right here, right now. If observation shapes reality, what does that say about the world you perceive? Is the solidity of your desk, the certainty of the ground beneath your feet, a kind of collective Zeno effect maintained by the constant interaction of countless particles? Do we, through our very presence, participate in freezing a shared reality into something stable and predictable? The universe, left to its own quantum devices, might be a seething, indeterminate fog. But we are never leaving it to its own devices. We are always measuring, always interacting, always observing. From the moment light bounces off an object and enters your eye, a chain of quantum interactions collapses into the classical world of your experience. You are not a passive spectator in a predefined universe. You are an active participant in its ongoing creation, a collaborator in a cosmic process that turns probability into actuality. This is not a call for mystical thinking, but a logical implication of our best scientific models. It suggests that the line between the physical world and the experience of it is far blurrier than we ever imagined. The Quantum Zeno Effect is more than a laboratory trick or an engineering principle. It is a tiny, precise window into a foundational mystery. What we see when we look deeply into the quantum realm is a reflection of our own role in the cosmos, endlessly asking questions of the universe and, in the very act of asking, changing the answers we receive. So the burning question remains, can we freeze reality on our own scale? Could you, in principle, use this quantum observation trick to stop a falling cup of coffee mid-air or pause a butterfly's wing in flight? The short, sobering answer is no, not directly. The quantum world is a realm of exquisite sensitivity, and our everyday world is a riot of noise and interaction. This is the problem of scale. To understand why, we need to think about a cat, not a real one, but the most famous feline in physics, Schrödinger's cat. In that thought experiment, a cat is placed in a box with a quantum device that has a 50-50 chance of releasing poison. According to the rules, until someone opens the box and looks, the cat exists in a superposition, simultaneously alive and dead. We never see this, of course. The cat is either purring or it is not. The reason we never see macroscopic superpositions, and by extension why we cannot easily freeze big objects with observation, is a process called decoherence. Imagine your quantum particle is a perfectly still, silent tuning fork. Now place that tuning fork in the middle of a roaring heavy metal concert. The delicate, pure note it holds is instantly drowned out by the overwhelming noise. That is what the warm, bustling world does to quantum states. A single atom can be isolated, cooled, and protected, but a coffee cup is made of trillions upon trillions of atoms, all jiggling with heat energy, constantly bumping into each other and interacting with air molecules and light. Each of these countless interactions acts as a kind of inadvertent measurement, constantly observing the system from the inside. This relentless environmental noise destroys quantum coherence almost instantly. The fuzzy probabilities collapse into a single, definite reality faster than you can blink. In such a system, trying to impose a quantum Zeno effect would be like trying to stop a stampeding herd by staring at a single cow. The scale is all wrong and the noise is far too great. Yet scientists are relentlessly pushing this boundary, trying to make quantum weirdness survive in larger and larger systems. They are not starting with cats, but with molecules. In recent years, experiments have successfully created quantum superpositions in molecules composed of thousands of atoms. These are still microscopic, but they are giants compared to a single atom. They achieve this by working in ultra-high vacuum, cooling the molecules to near absolute zero and isolating them from all possible disturbance. It is a monumental engineering challenge to create a pocket of silence quiet enough for quantum notes to ring out. Another frontier uses fabricated quantum systems like superconducting circuits. These are not single particles, but tiny loops of wire cooled to such extreme temperatures that electrons can flow without resistance, collectively behaving like a single, giant artificial atom. These circuits can be put into superpositions of having a current flowing clockwise and counterclockwise at the same time. They are macroscopic in size, sometimes visible to the naked eye, yet they obey quantum rules. Here, scientists actively combat decoherence using the very principles we have discussed, applying precisely timed pulses of energy to reset the system and protect its fragile quantum state. It is a direct technological application of the Zeno principle on a scale far larger than a single atom. So where does this leave our dream of freezing everyday reality? The direct, conscious control over macroscopic objects remains firmly in the realm of science fiction. You will not be stopping bullets in mid-air with a focused gaze. But in a deeper, more fundamental sense, the principles are already at work all around you and within you. The solidity of the floor, the predictable swing of a pendulum, the consistent burn of a light bulb, all these everyday stabilities emerge from the collective behavior of countless quantum particles. Their apparent stillness is the end result of a constant, dizzying dance of interactions and mini-collapses. While you cannot freeze a cat, the components that make up the cat and everything else are governed by these quantum rules. Our classical, predictable world is not separate from the quantum realm. It is what rises from it, like a still ocean surface emerging from the frantic motion of countless waves. The magic is not in scaling the trick upward, but in recognizing that the trick is the foundation of everything already running everywhere all the time. Yet the quantum world may not be confined to the cold silence of a vacuum chamber. There is a growing suspicion that life itself has learned to dance with these strange rules. A new frontier called quantum biology asks a revolutionary question. What if nature, over billions of years of evolution, has become a master of quantum mechanics? The evidence is mounting in the most ordinary of places, a sunlit leaf. Photosynthesis, the process by which plants convert sunlight into chemical fuel, is astoundingly efficient. When a photon of light strikes a leaf, it is absorbed by a network of chlorophyll molecules. The energy from that photon, called an exciton, needs to travel to a specific reaction center to be used. Classically, you would expect this journey to be a random walk, a haphazard bouncing from molecule to molecule, losing precious energy as heat along the way. But experiments suggest something far more elegant. The exciton seems to explore multiple pathways through the molecular network simultaneously, using quantum superposition to find the most efficient route. It is as if the energy is taking all possible paths at once, then choosing the quickest one. This quantum coherence, however, should be destroyed instantly by the warm, wet, and chaotic environment inside a living cell. So how does the plant protect it? This is where a Zeno-like mechanism might come into play. The molecular structures involved in photosynthesis are not passive wires, they are dynamic and vibrate in specific rhythms. Some researchers propose that these vibrations act as a form of continuous, gentle measurement. They constantly interact with the traveling energy, not enough to fully collapse its quantum state, but just enough to nudge it, guide it, and protect its coherence from disruptive noise. It is nature's version of dynamical decoupling, using the architecture of life itself to perform a quantum computation in broad daylight. The plant may not be observing in a conscious sense, but its very structure creates an environment where measurement-like processes sustain a quantum advantage. This turns the classic problem on its head. In the lab, we fight to protect quantum states from the environment. In the leaf, the environment might be actively engineered to protect the quantum state. Could a similar principle be at work in our own bodies? Consider the enzymes that catalyze the chemical reactions essential for life. They work with a speed and precision that defies classical explanation. One theory suggests enzymes might use quantum tunneling, allowing particles to pass through energy barriers as if they were ghosts walking through walls. For such a delicate process to work reliably in the messy cellular soup, some form of stabilization would be needed. Perhaps the enzyme's own structure, its specific folds and pockets, creates a sheltered quantum corridor with constant vibrational interactions that act like a Zeno guard, ensuring the tunneling particle stays on its ghostly path until the reaction is complete. Even more mysteriously, look to the sky. The humble European robin undertakes a migration of thousands of miles, navigating with pinpoint accuracy. Scientists have strong evidence that these birds use the Earth's magnetic field as a compass. But the mechanism is not based on a tiny piece of magnetic metal like a compass needle. Instead, it is believed to involve a quantum process in the bird's eye. Light strikes a molecule called cryptochrome, creating a pair of molecules in a quantum-entangled state, their fates linked across space. The Earth's magnetic field subtly influences the chemistry of this entangled pair, and the bird's visual system is sensitive to the outcome. For this to work, the fragile quantum entanglement must survive for a remarkably long time, possibly microseconds, in a biological environment. How? Again, the answer may lie in a protective Zeno-like scheme. The complex molecular environment around the cryptochrome could be providing a kind of rhythmic screening, a series of interactions that repeatedly reset the system against decoherence, just long enough for the bird to read the quantum magnetic map. If true, this means a robin flying at dawn is relying on a sustained quantum superposition to find its way. These are not settled facts, but thrilling lines of inquiry. Quantum biology suggests the boundary between the quantum and classical worlds is porous, especially where life is concerned. Nature may not be using conscious observation, but it appears to have evolved structures that harness measurement-like interactions to control and exploit quantum phenomena. The Zeno effect, from this perspective, is not just a laboratory tool or a philosophical puzzle. It could be a fundamental design principle in the living world, a hidden rhythm that helps turn probability into purpose and uncertainty into unerring navigation. Life may have been doing quantum engineering for billions of years, long before we ever thought to cool an atom with a laser. The connection between a frozen atom and your own sense of time is not as distant as it seems. Our personal reality is not just shaped by external clocks, but by the internal rhythm of our attention. Psychological studies reveal a fascinating parallel. When we are intensely focused on a task or in a state of high alert, our perception of time often slows down dramatically. Think of a car accident where seconds stretch into what feels like minutes, or an athlete in the zone where the ball seems to hang in the air, granting an eternity to react. This subjective time dilation is a well-documented trick of the mind. Neuroscientists believe that during these heightened states, our brain goes into overdrive, processing sensory information at an incredible rate and laying down dense, detailed memories. When we look back on that moment, the richness of the recorded data makes it feel like it lasted much longer than the clock would say. This is where a speculative yet irresistible analogy emerges. Just as frequent quantum measurements can freeze a particle in its starting state, could our own focused, conscious observation act as a kind of mental measurement? Could the laser-like beam of our attention, when held steadily on the present moment, alter our neural processing in a way that subjectively dilates time? It is as if by observing our own experience with unwavering intensity, we are performing a psychological Zeno effect, pinning our perception to a richer, more detailed slice of reality and momentarily slowing its apparent passage. This idea transforms from a laboratory phenomenon into a tool for living. It touches the heart of practices like mindfulness and the coveted flow state. Mindfulness is the deliberate, non-judgmental focus on the present moment. By continually bringing your attention back to your breath, a sound, or a sensation, you are effectively performing repeated measurements on your own conscious state. You are not allowing your mind to automatically decay into its usual patterns of rumination about the past or anxiety about the future. You are holding it gently but firmly in the now. The result is often a profound sense of time expanding, of moments gaining weight and clarity. Similarly, in a flow state, your attention is so completely absorbed by a challenging, rewarding activity that self-consciousness falls away. You are in a continuous feedback loop with the task, a constant observation of action and result that creates a timeless bubble. In both cases, mastery of attention creates a subjective reality that feels richer, slower, and more vivid. While we are not literally freezing quantum particles in our brains, we may be engaging in a cognitive process that mirrors the effect's outcome, a stabilization of experience. This suggests a futuristic lifestyle concept that is already within our grasp: personal time manipulation. It is not about building a time machine, but about engineering your own focus. In a world of endless distractions and fragmented attention, the ability to consciously direct your awareness becomes a superpower. It is the closest we might ever get to freezing a piece of our personal reality, to stretching a moment of joy, deepening a conversation, or fully inhabiting a creative breakthrough. The ultimate implication is that the quality of our time may be far more malleable than its quantity. By learning to observe our inner world with the same precision that a physicist observes a trapped atom, we might not change the clock, but we can fundamentally change the experience the clock is measuring. The ultimate promise of this quantum control is a revolution in how we build the world, molecule by molecule. Picture a future chemistry lab, but not one filled with bubbling beakers and the smell of solvents. Instead, it is a quiet, clean room where lasers hum. Here, chemists are not just mixing ingredients and hoping for the best. They are using the principles of the Quantum Zeno Effect to actively steer chemical reactions at the most fundamental level. This emerging field is called quantum control, and it aims to turn chemistry from a statistical art into a precise, digital craft. At the heart of every chemical reaction are bonds breaking and forming between atoms. These bonds are not little sticks, they are quantum mechanical relationships governed by the same probabilistic rules that allow an atom to be in two states at once. During a reaction, molecules pass through a fuzzy, in-between state called a transition state, a fleeting quantum superposition where old bonds are weakened and new ones are not yet set. This is the most critical and most uncontrollable part of the process. It is where unwanted byproducts often arise. Traditional chemistry tries to influence this by changing temperature, pressure, or catalysts, nudging the statistics in a favorable direction. But quantum control proposes something far more direct. What if you could use a laser to constantly observe that transition state? the idea is to design a sequence of laser pulses that interact specifically with the molecules as they attempt to form an unwanted pathway. Each laser pulse acts as a measurement, asking the system, "Are you heading down the wrong road?" If the answer is yes, the quantum interaction collapses the system's wave function, effectively resetting it and giving it another chance to choose the correct path. By frequently and precisely applying these laser questions, you could use a Zeno-like suppression to freeze out the undesired reaction channels entirely. It is like standing at a fork in a road and shining a blinding light down the path you do not want travelers to take, forcing everyone back to the junction until they finally take the only illuminated route you desire. The goal is absolute precision. This would mean chemical synthesis with near 100% yield, creating exactly the target molecule and nothing else. The implications are staggering for creating a new generation of green chemistry. Imagine pharmaceutical manufacturing that produces life-saving drugs without toxic solvents or hazardous waste. Consider the production of revolutionary new materials like superconductors that work at room temperature or ultra-efficient solar cells, all built with atomic precision because every bond was placed with intention. This is not just about efficiency, it is about a fundamental shift from brute force to elegant guidance. We move from heating a whole pot of soup and hoping the right ingredients combine, to using tiny, intelligent tweezers to assemble each molecule by hand, guided by the constant, watchful light of a laser. That light becomes more than a tool, it becomes the architect of matter itself. This quantum control over atoms gives us more than just better clocks, it offers a new way of seeing the world. The very sensitivity that makes quantum systems so fragile can be turned into an extraordinary strength. This is the frontier of quantum metrology, where the act of observation becomes a tool for sensing forces so faint they were once invisible. The principle is a beautiful inversion of the classic Zeno experiment. Instead of using frequent measurements to freeze a system in place, we use them to track its most subtle movements. Imagine a perfectly still, silent pond. If you toss a single grain of sand into its center, the ripples that spread outward are tiny, but they are there. Now imagine you could take a rapid series of photographs of the pond's surface, each one capturing the precise shape and position of those ripples as they expand. By comparing those snapshots, you could deduce not only that the grain of sand fell, but exactly how heavy it was and where it landed. Quantum metrology works on a similar principle, but the pond is a prepared quantum state, and the ripples are changes in its delicate superposition. Scientists begin by placing a collection of atoms, ions, or specially designed circuits into a highly sensitive, balanced quantum state. This is like balancing a pencil perfectly on its tip, a precarious condition that reacts to the slightest breeze. Any external influence, a whisper of a magnetic field, the faint tug of a gravity wave, or the passage of an elusive dark matter particle, will nudge this quantum pencil. It will begin to tip, causing its wave function to evolve in a predictable way. Here is where the magic of measurement comes in. By frequently but carefully probing this quantum system, scientists can take a series of snapshots of its evolution. They are not trying to freeze it, they are watching it fall with exquisitely precise timing. Each measurement extracts a tiny bit of information about the external force acting upon it. When all these data points are combined, they reveal a signal that will be completely drowned out in a classical sensor. It is like listening to a single instrument in a symphony by focusing your ear so precisely that you can follow its melody through the noise. The potential applications read like a catalog of tomorrow's discoveries. In medicine, this could lead to a revolution in brain imaging. Current machines like MRI scanners are massive, requiring powerful magnets and cooling systems. A quantum sensor based on these principles could be miniaturized, perhaps even to a wearable device. It would be sensitive enough to map the incredibly faint magnetic fields produced by individual neural firings in real time. giving us an unprecedented window into the living, thinking brain without invasive procedures. Geologists could use arrays of such sensors to detect subtle gravitational variations underground, pinpointing mineral deposits or monitoring the movement of magma beneath volcanoes with a clarity we can only dream of today. But perhaps the most profound use lies in the search for the universe's deepest secrets. Fundamental physics experiments are constantly pushing the limits of measurement to test our theories. The search for gravitational waves, ripples in space-time itself, is a prime example. These waves stretch and compress space as they pass, an effect so minuscule it is like changing the distance to the nearest star by the width of a human hair. Detecting them requires almost unimaginable sensitivity. Quantum-enhanced sensors operating at the limits imposed by the Zeno principle could form the next generation of observatories. They might be deployed in space as silent sentinels, listening for the echoes of black holes colliding at the edge of the cosmos. Even more speculatively, such devices could be our first trap for dark matter. If dark matter particles interact with ordinary matter at all, the effect would be incredibly weak. A sensor that can detect the quantum nudge from a single, passing particle would be our only hope of finally seeing the unseen majority of our universe. This transforms the observer's role once more. We are no longer just freezing reality or accelerating it. We are using quantum vigilance as a kind of super-powered hearing aid, listening to the faintest whispers of the cosmos, whispers that tell us what the universe is made of and how it truly behaves. Light itself can be frozen. This is not science fiction, but a direct application of the Quantum Zeno Effect in the world of photonics, the science of guiding and manipulating light. Just as we can pin an atom in place with repeated questions, we can trap a particle of light, a photon, in a prison of its own making. The stage for this feat is not a vacuum chamber, but a photonic cavity, a microscopic structure designed to confine light. Imagine a tiny hall of mirrors, so perfect that a photon can bounce back and forth for an astonishingly long time. But even the best mirrors are not perfect. Eventually, the photon will leak out, it will escape its prison. This escape is a quantum process, a probabilistic decay from a high-energy state of having a photon to a low-energy state of having none. And where there is a quantum process, the Zeno principle can apply. The trick is in how you measure a photon without destroying it. You cannot shine a light on light. Instead, scientists use a clever proxy. They couple the main cavity, the one holding the photon, to a second ancillary system. This second system acts as the observer. By frequently checking the state of this ancillary system, you indirectly probe the main cavity. Each check, each coupling event asks the question, is the photon still here? If the answer is yes, the system is projected back to its starting state. The photon's wave function, which was beginning to evolve toward escape, is reset. By performing these indirect measurements rapidly enough, you can suppress the photon's natural tendency to leak out. You freeze it inside the cavity, not with physical walls, but with information. The photon becomes a prisoner of observation, its escape route constantly blocked by the actor being watched. This ability to trap light on demand opens doors to revolutionary technologies. The most immediate is an all-optical switch, a device that controls one beam of light with another. In a Zeno-based switch, a faint control laser could act as the observer. By pulsing this control beam, you could decide whether to let a signal photon proceed down a fiber or trap it in place, creating a logic gate for light that operates at the speed of light itself with minimal energy loss. More profoundly, this becomes a memory for light. In the quest for a quantum internet, information would be encoded in fragile quantum states of photons. But you cannot store a photon in a hard drive. You need a way to capture it, hold it perfectly still, and release it on command. A Zeno-trapped photon in a cavity is exactly that, a quantum memory. Information carried by light could be frozen in a node, held securely until it is needed for the next step in a calculation or transmission across the network. This transforms the cavity from a simple mirror box into an active component of a thinking network. Furthermore, by combining multiple such cavities, you could create circuits where light is routed, processed, and stored according to quantum logic. The dream of a quantum internet where unbreakable encryption and distributed quantum computing become possible relies on this mastery over individual photons. It requires not just sending light, but taming it, convincing it to pause and wait. The same principle that seemingly halts time for a quantum particle may one day provide the heartbeat for a global network of connected quantum minds, where the currency of information is not electrons, but frozen light, patiently waiting in the dark for its moment to shine again. But these abilities come wrapped in a profound logical knot. The Quantum Zeno Effect does not just describe a process, it creates a paradox about the nature of reality itself. If constant observation can freeze a system, and measurement is what collapses possibilities into facts, then a startling implication emerges. It suggests that change at its most fundamental level might only be possible when we are not looking. The universe, in this view, evolves in the gaps between our glances. It is as if reality is a shy performer who only dances when the audience closes its eyes, freezing into a still pose the moment the house lights come up. This is the core of the Quantum Zeno paradox, a logical hall of mirrors that challenges our intuition about cause and effect. We are forced to ask, does the moon exist when no one is looking at it? Quantum mechanics, through this lens, suggests it might not exist in a definite state at all, but rather as a cloud of potential positions and motions that only snap into the familiar, singular moon when observed. The Zeno effect takes this idea to an extreme, proving that if you look too often, you can prevent that cloud from ever shifting at all. You can, in essence, trap the universe in a single moment of your own choosing through the sheer persistence of your attention. This transforms observation from a passive act of discovery into an active force of creation and preservation, placing the observer in a role of dizzying responsibility. The line between watching the world and building it begins to dissolve. This paradox is not merely philosophical, it has a precise and powerful twin in engineering. If the standard Zeno effect uses frequent measurement to suppress change, its logical counterpart, often called the anti-Zeno effect or bang-bang control, uses it to accelerate change. The name bang-bang comes from control theory, describing a system that is switched abruptly between two states, like a thermostat that is either fully on or fully off. In the quantum version, you do not just observe the system, you hit it with a rapid, timed sequence of control pulses. Instead of gently asking if it has changed, you aggressively push it toward the change you desire. Each pulse is like a perfectly timed kick to a swinging pendulum. If your kicks are out of phase, you can stop the swing. That is the freezing Zeno effect. But if your kicks are perfectly in phase, synchronized with the pendulum's natural rhythm, you add energy with each push. You make it swing higher and higher, faster and faster, until it completes a full transition in record time. This is not a violation of the paradox, but its completion. It proves that the observer's influence is not one-dimensional. We are not just guards at the gate of reality, we are also its architects. By choosing the rhythm and intent of our interaction, we can decide whether to lock a quantum door shut or blow it off its hinges. This bang-bang control is the principle behind some of the most precise manipulations in quantum computing, where qubits must be flipped from 0 to 1 and back again with flawless timing. It shows that the power granted by the paradox is not just to stop time, but to master its tempo. The strangeness deepens with a concept that seems pulled from a ghost story: interaction-free measurement. This is a quantum protocol so counterintuitive it allows you to detect an object without a single particle from your probe ever touching it. The most famous illustration is the Elitzer-Weidmann bomb tester. Imagine you have a collection of incredibly sensitive bombs, so sensitive that if a single photon of light strikes one, it will explode, but some of the bombs are duds with broken triggers. Your task is to find a working bomb without setting it off. Classically, this is impossible. Any attempt to look at the bomb would destroy it. Quantum mechanics, however, provides a ghostly solution. You set up a mock Zeno interferometer, a device that splits a single photon into two paths that later recombine. In one path, you place the bomb. If the bomb is a dud, it does nothing, and the photon behaves like a wave. The two paths interfere with each other, and the photon always emerges from a specific output port. Let us call it port A. But if the bomb is live, its presence fundamentally changes the experiment. The photon, as a wave, travels both paths simultaneously. On the path with the bomb acts as a detector. The mere possibility of interaction with the live bomb collapses the photon's wave function. It is as if the bomb sees the photon, even though no explosion occurs. This collapse destroys the delicate wave interference. Now, when the paths recombine, there is a chance the photon will emerge from a different port B. So, if you send a photon and it comes out of port B, you know with certainty that a live bomb is in the path, and you have learned this without the photon ever physically triggering it. The bomb was detected by its potential to interact, by the shadow it casts on the quantum world. This is not magic, it is a direct consequence of measurement-induced collapse. The bomb, by being a possible observer, changes the behavior of the photon from afar. What does this tell us about the Zeno paradox? It blurs the line between observation and interaction until they are almost indistinguishable. In the bomb tester, the object of interest is detected because it could measure the photon. Its very existence as a potential observer changes the outcome. This forces us to refine what we mean by looking. It is not about human eyes or conscious awareness. It is about any process that can extract information, that can cause a quantum possibility to resolve into a fact. A live bomb is a detector. A photon hitting a camera sensor is a detector. The warm, noisy environment is a ceaseless detector. The universe is filled with observers in this quantum sense, all constantly interacting and collapsing each other's wave functions. This is why macroscopic objects appear stable and definite. They are under continuous observation by everything around them, locked in a collective Zeno effect that freezes them into the familiar reality we experience. The paradox then softens but does not disappear. Reality does change when we are not looking, but we is not just you and me. It is the cosmos itself, engaged in an endless, intricate dance of mutual measurement. The profound takeaway is that isolation is the key to quantum possibility. To see the universe dance its strange, probabilistic dance, we must give it a moment of privacy, a quiet corner away from the relentless gaze of other things. And when we learn to control that gaze, to switch it on and off with the precision of a laser pulse, we gain the power to invite the weirdness out into the open, to freeze it, to accelerate it, or to ask it ghostly questions that reveal secrets without ever touching a thing. Think of a coin spinning on a table. In our everyday world, it is a simple object obeying simple rules. It spins for a while, wobbles, and eventually lands with either heads or tails facing up. The outcome is a perfect 50-50 chance, a symbol of pure randomness. Now, let us shift perspective. Imagine you could see that coin not as a solid disk, but as a quantum object. While it spins before it lands, it is not definitively heads or tails. It is in a superposition of both, a ghostly blend of possibilities. Its fate is undecided. This is the quantum state we are trying to understand. Now, here is the thought experiment. Instead of letting the coin spin freely to its conclusion, you become an incredibly fast, incredibly impatient observer. The moment it starts spinning, you slam your hand down on it. You check, is it heads? Let us say it is. You lift your hand and the coin, slightly jostled, begins to spin again from that heads-up position. Almost instantly, you slap your hand down again. Check. It is still heads. Lift, spin for a fraction of a second. Slap. Check. Heads again. You repeat this process with blinding speed, never allowing the coin to complete even a single full rotation in private. What happens? The coin never gets a chance to explore its other possibility, tails. It is frozen by your constant intervention in the head state. Each slap is a measurement. Each measurement collapses the coin's fuzzy potential back into the concrete reality you just observed. You are resetting the spin clock with every interruption. This is the heart of the Quantum Zeno Effect, translated into a macroscopic, intuitive picture. Your hand is the laser pulse. The coin's natural tendency to flip and eventually land is its quantum evolution. Your obsessive slapping is the frequent measurement that inhibits that evolution. Of course, a real coin is not a quantum system. It is far too large and noisy. Decoherence from the air and the table settles its fate almost instantly, but the logic of the analogy holds perfectly. The act of looking, when done relentlessly, does not just reveal reality, it can actively preserve a particular version of it. It stops the story from turning the page. This mental model helps us grasp why scientists firing lasers at an atom can keep it excited, or why a carefully timed sequence of pulses can protect the fragile state of a qubit. The universe, it seems, allows for a strange kind of stasis, a pause button that is triggered not by a lack of time, but by an excess of attention. The coin frozen under your hand presents a powerful but perhaps misleading picture. It suggests a conscious observer holds the power, yet within the physics community, this interpretation sparks intense debate. A significant school of thought argues the Quantum Zeno Effect has little to do with consciousness or even observation in a philosophical sense. Instead, it is about raw physical disturbance. In the lab, measurement is never a passive glance. That laser pulse hitting the atom is a blast of electromagnetic energy. Coupling a qubit to a readout circuit injects electrical noise. These are violent interventions, not gentle inquiries. Critics contend that what freezes the system is not the act of knowing, but the brute force impact of the measurement tool itself. The laser pulse does not ask a question, it shoves. It continuously pumps energy into the atom, overwhelming its natural tendency to decay. From this viewpoint, the effect is less a paradox about reality and more a straightforward engineering result of incessant kicking. This demystifying perspective is crucial. It shifts the narrative from mind over matter to matter interacting with matter in a predictable, if complex, way. The observer is demoted from a mystical participant to a physical apparatus that unavoidably alters what it touches. This leads us to a deeper, more nuanced model known as the dynamical Quantum Zeno Effect. Here, the freezing does not come from a series of sharp, discrete slaps or measurements. It emerges from a continuous, strong interaction between the system and its environment. Imagine our spinning coin again, but this time, instead of slapping it, you press your palm firmly against its edge, holding it upright as it spins. You are applying constant, unyielding pressure. The coin cannot fall to heads or tails because your hand is always there, a physical barrier that dictates its state. In the quantum realm, this is akin to an atom being bathed in an intense, continuous laser field tuned to its excited state. The atom is so powerfully coupled to this field that it simply cannot transition. It is locked in place by an unbroken interaction. The discrete measurements of the standard Zeno effect are just a specific, pulsed version of this more general dynamical suppression. This distinction is not just academic, it reshapes the philosophical implications. If the effect works just as well through constant force as through periodic checks, then the special role of the measurement and its associated collapse of the wave function becomes less central. The magic seems to drain away, replaced by the mechanics of coupling and control. This does not make the phenomenon any less astonishing or useful, but it does ground it firmly in the world of physical forces. It suggests that pop science narratives, which often lean into the mystery of the conscious observer, might be selling a more romantic, less accurate story. The truth appears to be both more mundane and, in its own way, more profound. Reality may be shaped not by our ethereal gaze, but by the tangible, energetic connections everything shares. The universe freezes not because it is being watched, but because it is constantly being touched, pushed, and held in an endless quantum embrace. This mechanical dance of interaction is what ultimately builds the stable world we perceive from the chaotic quantum fog. The stability we engineer today hints at a future where power itself is reimagined. A new frontier in energy storage is emerging from these quantum principles, the concept of a quantum battery. This is not a smaller lithium cell, but a device that operates on an entirely different set of rules, harnessing collective quantum effects to achieve what seems impossible. The core idea is entanglement and superradiance. In a classical battery, energy is stored in the chemical bonds of many independent molecules. In a quantum battery, the storage units, perhaps atoms or artificial atoms called quantum dots, would be quantum mechanically entangled. Their fates would be linked, not separate. This collective state allows them to absorb energy not as individuals, but as a unified whole, a phenomenon known as superradiance. It is the difference between filling a swimming pool with a single garden hose and opening a floodgate. Theoretically, such a battery could charge not just linearly faster, but at a rate that scales with the square of the number of quantum units, leading to near instantaneous charging. But this incredible potential is also its greatest vulnerability. The entangled, high-energy state is exquisitely fragile. The slightest interaction with the environment would cause decoherence, collapsing the useful quantum state and leaking the stored energy as useless heat almost immediately. This is where the Guardian principle steps in. To make a quantum battery practical, you would need to protect its charged state with something like a Quantum Zeno Effect. The battery's full, entangled condition would be its excited state. A network of subtle, constantly active sensors would monitor the system, not to drain it, but to guard it. These sensors would perform frequent, gentle measurements designed to detect the earliest signs of decoherence, the first whisper of a quantum unit trying to decay and break the entanglement. Upon detection, a feedback mechanism would apply a tiny, corrective pulse of energy, effectively projecting the system back to its perfect, fully charged configuration. It would be a continuous, automated act of quantum vigilance, using observation not to drain the battery, but to freeze it in its peak condition. The charged state would be locked in place, immune to the natural leakage that plagues all current batteries. The power would be preserved perfectly until the moment you flip a switch. Then, the protective Zeno field would disengage, allowing the entangled units to release their energy in a synchronized superradiant burst. The result would transform daily life. Your electric vehicle could charge from empty to full in the time it takes to plug it in. A laptop or phone charged for seconds could operate for weeks without ever touching a cord. The entire energy grid could balance itself with banks of quantum batteries, absorbing surplus solar and wind energy instantly and releasing it on demand without loss. This vision moves energy storage from the realm of chemistry into the domain of information and control. The battery no longer just holds electrons, it preserves a quantum state. It is a future where the very act of preventing change becomes the source of enduring power, a beautiful paradox made real by our growing command over the quantum world. This immense power to freeze and shape reality does not arrive without profound questions. The very principle that promises such control, the idea that observation can dictate a system state, carries a heavy ethical weight. We are moving toward technologies that operate at the most fundamental layer of existence, and with that comes a responsibility we have never before had to consider. If we can use quantum observation to lock a particle in place, could we, in theory, develop observation on a scale that locks something far more complex in place? The specter of surveillance emerges not just of actions or communications, but at a quantum level. Imagine sensors so sensitive they could detect the faint magnetic signatures of individual thoughts forming in the brain, or devices that could infer your private state by the quantum disturbances in the space around you. This is not about reading your emails, it is about potentially reading the ambient quantum noise your very presence creates. It is a surveillance of reality's substrate, a watching so deep it could make the concept of privacy seem quaint. The ethical framework for such power does not yet exist. We would be building tools that challenge the very notion of an unobserved moment, of a private thought, because at the quantum level, observation is interaction. It is not a camera on a street corner, it is a hand on the shoulder of the universe, and we must decide when that hand has a right to be there. This connects directly to a modern phenomenon we all live with, the social media observer effect. You know how it feels when you are aware that your actions are being watched, recorded, and quantified. Your behavior changes. You curate your life, you perform a version of yourself optimized for an audience. This is a macroscopic, psychological echo of the Quantum Zeno Effect. The constant gaze of the platform through likes, shares, and metrics acts as a form of continuous measurement. It can freeze you into a particular identity, discouraging natural evolution or the exploration of unpopular ideas for fear of social decoherence, of collapsing out of favor. The platform's architecture is designed to be the laser pulse, constantly asking, are you still engaging? Are you still relevant? And resetting your engagement patterns accordingly. This observation is not neutral, it shapes the reality of the digital self. Now, extrapolate that principle to a future where the observation is not just of your clicks, but of your biological and quantum environment. The ethical dilemma magnifies 1,000-fold. Who controls the observers? What are they allowed to measure? And if measurement is control, who gets to decide what version of reality is frozen into place? Is it a collective democratic process, or does this power concentrate in the hands of a few who understand the underlying technology? The philosophy here is staggering. A science that suggests reality is malleable to our gaze ultimately suggests that power belongs to those who control the gaze. This moves beyond physics into the realms of governance, equity, and human rights. It forces us to ask if some aspects of reality should remain unobserved, untouched by our controlling light, to preserve the natural, unpredictable flow of life and thought. The quantum world teaches us that isolation is necessary for possibility. Perhaps ethically, we must design pockets of guaranteed quantum privacy into our future, not just for data, but for the human spirit, ensuring there are always corners of existence where the universe, and we along with it, can dance unseen. The idea that looking can freeze reality is a story we have always loved to tell. Science fiction has long been fascinated with this power, often stripping away the complex physics to reveal a potent narrative core. In the film The Matrix, reality itself is a digital simulation, but the most iconic scenes play with the rules of observation. When Neo begins to see the code beneath the world, he learns to dodge bullets not because he moves faster, but because he perceives time differently. In that moment of hyper-focused awareness, the bullets seem to hang in the air, their progression arrested. It is a cinematic metaphor for a psychological Zeno effect, where the mind's intense observation of a threat subjectively stretches and controls time. The movie literalizes the feeling we all know, that moment of crisis where everything slows down, and suggests that mastery comes from mastering your own perception, from becoming the ultimate observer of your own reality. Another classic trope, the stasis field or freeze ray, appears everywhere from comic books to episodes of Doctor Who. A device is activated and everything in a bubble of space is frozen in time, people caught mid-step, droplets of water suspended in air. While these fictional fields stop all molecular motion, a far cry from suppressing a quantum transition, They capture the visceral human desire behind the Zeno principle, the wish to pause the world to create a perfect, unchanging moment. These stories ask what we would do with such control and what it would cost us. They explore the loneliness of being the only moving thing in a frozen world, highlighting that observation in these tales is often a solitary and burdensome power. The most enduring philosophical question tied to observation is the old thought experiment. If a tree falls in a forest and no one is around to hear it, does it make a sound? Philosophy traditionally debated whether perception is necessary for qualities like sound to exist. Quantum physics injects a startling new twist into this centuries-old puzzle. It suggests a more fundamental question: if a tree falls in a forest with no observer present, does it fall in a definite way at all? Before an interaction, a measurement, the tree and its falling state might exist in a haze of potential. The crash, the splintering of wood, the compression of air into sound waves, all these events require a chain of definite interactions. Without an observer, which in the quantum sense could be anything from a stray photon to a rock on the ground, the argument is that the entire event remains in an unresolved superposition of possibilities. It is not about the sound, but about the fact of the fall itself. Science fiction writers have latched onto this implication with glee, crafting stories where reality is fluid until a conscious mind pins it down. This transforms the observer from a witness into a creator, a godlike figure whose attention births the world moment by moment. While actual quantum effects are negligible at the scale of trees and forests, the conceptual bridge is powerful. It takes a complex, counterintuitive scientific principle and plants it firmly in the human imagination, allowing us to play with the terrifying and thrilling idea that our gaze is not just recording history but writing it with every glance. The power to shape quantum reality is no longer locked in a distant laboratory. You can reach out and touch these principles yourself from your own computer. Online platforms have flung open the doors to the quantum world, inviting anyone with curiosity to step inside. One of the most remarkable is the IBM Quantum Experience. This is not a simplified animation, it is a portal to real quantum hardware and powerful simulators. You can drag and drop graphical elements to build quantum circuits, the blueprints for computation. Here you can directly test the ideas we have been exploring. You could design a simple circuit that prepares a qubit in a superposition, that ghostly blend of 0 and 1. Then you can add a series of measurement gates. By placing these measurement points very close together in your circuit's timeline, you are instructing the simulator to repeatedly ask the qubit for its state. Run the experiment and you will see the statistics. With frequent measurement, the qubit's chance of flipping to the opposite state drops dramatically. You are not just reading about the Quantum Zeno Effect, you are orchestrating it with a click, watching the abstract principle translate into concrete data on your screen. It is a profound democratization of knowledge, turning the most esoteric physics into a hands-on workshop. For a more narrative-driven exploration, look to the world of advanced video games. Titles like Quantum Chess or the puzzle game Qubit are built from the ground up on the actual mathematics of quantum mechanics. In quantum chess, pieces can exist in superpositions, occupying multiple squares at once until you move to capture one, forcing a collapse. You must think in terms of probabilities and entanglement, developing an intuition for how observation changes the game board. It is training for a new kind of logic, where the simple act of looking is your most powerful and dangerous move. These are more than games, they are interactive textbooks that build understanding through strategy and consequence. You do not even need a computer to begin bending your mind around these concepts. A simple thought experiment with a flashlight and a mirror can illuminate the strange role of the observer. Shine a flashlight at a mirror in a dark room. The beam reflects and you see a spot of light. Now consider what is happening at the quantum level. That beam is made of countless photons. Each photon, as a particle, could be said to hit a specific point on the mirror. But as a wave, it actually interacts with the entire surface of the mirror at once. The mirror, by reflecting it, is performing a kind of measurement, forcing the photon's wave to collapse into a definite path to your eye. The spot of light you see is the result of trillions of these tiny quantum collapses happening continuously. Your eye is the final observer in a long chain, but the process begins with the physical interaction at the mirror. This reframes a mundane event into a quantum phenomenon happening in real time on your wall. To feel the weight of measurement, try a social experiment. The next time you are in a meeting or a classroom, pick a quiet moment and simply stare intently at the back of someone's head. Do not say anything, just observe with focused attention. More often than not, the person will eventually turn around, sensing the pressure of your gaze. While this is likely due to subtle cues or psychological sensitivity, it is a tangible metaphor for the disturbance caused by observation. Your look is not a neutral act, it transmits a kind of social energy that provokes a reaction. It is a macroscopic echo of the quantum truth that to look is to interact, and to interact is to change what you see. These gateways, from professional simulators to kitchen table analogies, serve a vital purpose. They dissolve the barrier between the awe-inspiring theory and your own intellect. Futuristic technology begins to feel less like magic performed by others and more like a new set of rules waiting to be learned. By engaging with these simulations and exercises, you are not just consuming information. You are practicing a new way of seeing the world. You are training your mind to hold two contradictory ideas at once, to accept probability as a physical reality, and to recognize yourself as an active participant in the unfolding of events. This is the first essential step toward a future where quantum thinking is not confined to physicists, but becomes a part of our shared toolkit for understanding reality itself. This crucial distinction is where the real magic of science separates from the seductive pull of pseudoscience. The Quantum Zeno Effect is a powerful, proven phenomenon, but its power is confined by very specific and unforgiving rules. It does not mean you can stop aging by staring intently into a mirror. The cells in your body are not isolated quantum systems waiting for your observation. They are bustling, warm, classical objects constantly measured and disrupted by their own internal noise. No amount of positive thinking or focused will can freeze an illness in place through quantum observation alone. The effect is not a psychological tool, it is a physical one, requiring a level of isolation and control that is utterly impossible for a human being to exert over their own macroscopic body. It operates in the realm of individual particles and precisely tuned lasers, not in the domain of conscious intention or belief. This is a vital boundary to understand. The genuine wonder of the Zeno effect has at times been co-opted by popular narratives that distort its meaning. You might hear it referenced alongside ideas like the law of attraction, where simply observing your desires is said to manifest them into reality. Or it gets tangled with the placebo effect, where belief in a treatment triggers real physiological improvement. While the placebo effect is a fascinating and real demonstration of the mind-body connection, it works through complex biochemical pathways in the brain and nervous system, not through the collapse of quantum wave functions. These are important psychological and biological phenomena, but they operate on a completely different scale and through entirely different mechanisms. Conflating them with quantum physics creates a kind of scientific soup where anything seems possible, which ultimately cheapens the profound and specific truth of each discovery. The real Zeno effect is not a metaphor for wish fulfillment. It is a mathematically precise prediction arising from the equations of quantum mechanics, confirmed under stringent laboratory conditions that are the opposite of everyday life. It requires a system that can be described by a quantum wave function, like a single atom or a superconducting circuit. It demands that the system is almost perfectly isolated from its environment, because any stray interaction acts as an unwanted measurement and ruins the experiment. And it hinges on the ability to perform measurements or apply control pulses with a timing and precision that borders on the unimaginable, billions of times per second in some cases. When these conditions are met, the freezing happens. When they are not, it does not. This is the rigorous, testable framework of science. Appreciating this rigor is what allows us to marvel at the effect without falling into magical thinking. The wonder is not that we can control reality with our minds, but that reality has this strange clockwork-like rule built into its deepest fabric, a rule we can uncover and use with the right tools. It means the universe is predictable in its strangeness, offering not limitless personal power, but a limitless curiosity to be satisfied. By holding this accurate understanding, we protect the integrity of an incredible scientific discovery. We ensure that the conversation stays grounded in what is real, so that the future we build, with quantum computers, unimaginable sensors, and new forms of energy, rests on a foundation of truth, not a fantasy of misinterpretation. The power of the Zeno effect is breathtaking precisely because it is true, and its truth is far more interesting than any myth we could invent. The journey from a Greek philosopher's paradox to a laser beam freezing an atom is a story of human curiosity at its boldest. We have traced a line from Zeno's mental dissection of motion through the profound mystery of quantum measurement to the stark, beautiful data from a trapped ion experiment. We have seen this principle harden into the technology of atomic clocks, guide the fragile hope of quantum computers, and whisper its possibilities in the machinery of life itself. This is not merely a collection of facts, but a single, expanding revelation about the nature of reality. The core takeaway, the thread connecting every part of this exploration, is that at the universe's most fundamental level, watching is never just watching. Observation is an action, a physical interaction that changes what it touches. Reality at the quantum scale seems less like a pre-recorded film and more like an improvisational dance where the steps are only determined as the dancers move together. Our glance is not a spotlight on a finished stage, it is a footstep that helps create the path. This transforms our role from distant spectators to intimate participants. The solid, predictable world we experience emerges from a ceaseless storm of these quantum interactions, a collective stability born from endless, tiny observations. The ultimate lesson of the Quantum Zeno Effect, then, may be one of profound connection. We are not separate from the universe, looking in from the outside. We are of it, and our every interaction, from a conscious thought to the passive detection of a photon, is part of the ongoing process that crystallizes probability into the moment we call now. We are collaborators in creation, partners in a cosmic dance where to observe is to engage, and to engage is to shape what comes next. What does that realization change for you? Share your most mind-blown thoughts in the comments below, and if you want to keep exploring the edges of reality with us, be sure to subscribe.